Hello all, welcome back. Today is lecture 38. So, including today we have 3 lectures remaining for silicon RF devices including LDMOS. So, what we will do today is we will briefly touch upon the noise of MOSFET, a generic MOSFET, okay, and then we will move to LDMOS, which is the high voltage counterpart for MOSFET. Okay. So, over to the whiteboard here. So, although we have talked about noise figure and noise quite a few times in our discussion for 3-5 devices, but it is important to take a more fundamental look at noise. So, what noise is essentially? So, noise is random, we know that noise is random, and as you can see the noise signal, this is the noise signal. With respect to time, the noise can have any arbitrary magnitude, in a sense that it is very random, it can go positive, negative, etc. And so, if you take the time average of the noise, it will basically cancel out, it will be like 0. So, you cannot predict the instantaneous value of noise, okay. The noise is purely random, but noise power is not random. The power that is essentially carried by the noise or that can be associated with the noise. So, what happens is that people take noise power, which is basically square of the noise, okay. So, if the noise signal is n of t, if you take square of that, you basically take only the squaring makes it essentially all positive, as you can see this, right. So, if you square the noise signal, you get the noise power, okay. That noise power and is represented by Pn is not actually random, fortunately, okay. And this noise essentially if we talk about the most common source of noise, which is thermal, okay. If you take any resistor R, okay, it can be even a semiconductor because it can be modeled as a resistor, okay. So, whenever there is a resistance R, electrons that are travelling will basically have thermal agitation, they will collide with other impurities or the electrons, phonons, atomic vibrations. So, their path will be random, electrons will go random. If you apply potential between A and B, electrons will move overall from A to B, but not in a straight path, they will go all random, but in general you can say that electrons are moving from say point A to point B. So, there you get a current there, but at a macroscopic scale the electrons are moving randomly, okay, because of the thermal agitation. So, at any temperature T, you will always have this thermal agitation, and so there will always be a noise that originates from this thermal, this resistance. So, this is thermal noise, which is the most common noise, okay, and because noise is random, it can go any value around the mean. So, we have to take the square of the noise. In that case, we can calculate the noise power, okay, the power that is associated with the noise, alright. So, if you for instance this is at a temperature of say 300 Kelvin, if you increase the temperature to say 400 Kelvin, then the overall collisions, the thermal agitation, etc. will increase. So, the noise power will increase because with higher temperature there will be more noise, more thermal noise, okay. So, the way to calculate the noise power is that you take the square of the noise the noise signal, and then you basically take the area under this noise signal over a very large period of time, and then you divide by the time, you normalize with respect to the time. So, this is what it does. So, this is the area of the noise power over a large amount of time, and then you time average it by t as t tends to infinity, okay. So, that is your noise power. Now, how long should this t be at limit of integration? See, in a way, if you, this is a time domain representation, but if you actually consider a frequency domain representation, then noise that will look like that in time actually consists of many frequencies, okay, it consists of many frequencies. So, the time period typically should be such that you take the lowest frequency signal that is there, which corresponds to the highest wavelength, okay. The time periods should be such that that lowest frequency or the highest wavelength signal completes a few cycles, okay, it completes a few cycles, that is the time of t. So, what do I mean? Suppose you go to a restaurant, where there are many people, they are talking, they are banging, they are shouting. So, typically human voice is from 20 hertz to 20,000 hertz, correct, that is the human audible. So, if and there is a noise, the noise that we can hear is also within this range. So, the lowest frequency here corresponds to 20 hertz, okay. So, 20 hertz means that it is 0.05 second. If I take 1 by f, then the period of the lowest frequency is 0.05 second. So, you can take 10 times that, so around 0.5 second. So, you can integrate over 0.5 second, okay, you can integrate the noise power over 0 of the human noise in this case over 0.5 second, and then you divide by 0.5 second, because this is about 10 times the inversion of the 10 times the lowest frequency, the time period corresponding to the lowest frequency, Okay. So that's a a representation of how much time you should take to average it out. In practice you may not know what the lowest frequency is in an RF system. So people basically guess the T, they find out the power, the noise power, then they increase the T, or sorry, they decrease the T, and they keep doing it until successively you get the same Pn, which means the time has no effect. So you know that that's the T that you should take, the good case of T you should take. So this is generally about noise, okay, the thermal noise, and in a way. So what is the message we carry? Noise is random, instantaneous value cannot be predicted. So you square the noise, so you get essentially noise power. That noise power, the average power of the noise is very much known, or it can be measured, it can be, it's constant, it's not random, okay, the noise power is not random, and that is something we deal with because that is very that helps understand and do many things about noise, the noise power, okay. This is generally true not only for MOSFET, in general for noise, okay. Now there is a very important thing in noise which is called the power spectral density. So what does power spectral density mean? It means that I take the power of noise, say, for every 1 hertz bandwidth. So if I take just a 1 hertz, suppose I measure it at 1 hertz, I measure it at 2 hertz, 3 hertz, but at every single frequency I measure the power of the noise, okay. In the crowded restaurant case, when people are shouting, talking, human voices are between 20 hertz to 20,000 hertz. So how can we calculate the power spectral density of the noise of human voices? So essentially at say 20 hertz, only at 20 hertz, nothing else, you take a filter, you filter out all other frequencies, you only take 20 hertz and find out what is the power of the overall noise, and you get some power, okay. Suppose that is P1. Then at 21 hertz, only 21 hertz, you get something P2. You keep doing that until 20,000 hertz. So what happens is that you get the power on the y axis, and on the x axis you have frequency from 20 to 20,000 for instance, and that looks something like that, okay. So maybe at certain frequencies the power is more, at certain frequencies the power is less. This is the power spectral density. You are basically taking it every single hertz, okay. This is how actually spectrum analyzer is going to work. You take it every single frequency and you find out the noise. You do not practically do it, but this is the representation, and that is your power spectral density. So the area under this actually is the noise power, which is Pn, and this is the area under that. Your frequency will go from 0 to infinity because any frequency can be there. This is also in the previous slide, if you see this expression is precisely this. So that is the area under this power spectral density, or it is the time average of the noise power density, okay. So that is your power density, okay. And for a resistance R, the thermal noise, it so happens is that it is 4 times K Boltzmann constant temperature times R. This is your noise, you can say the noise, actually the unit of this is actually Vn square, the noise voltage square. This is the noise voltage square that you are generating for a resistance R. Many textbooks also give a delta F with it, multiply it by a delta frequency over which you are considering, but here we can say that we are normalizing with respect to the frequency at every hertz. So essentially it will be volt square by hertz, that will be the unit of the power spectral density, okay. It is the power spectral, that average the noise voltage by power spectral density, okay. And if you want to represent the noise voltage, it will be square root of that, which will be volt by square root of hertz. Now square root of hertz looks very bizarre, but actually it has no worry, we do not have to worry. It basically means that if I have say 1 nanovolt per square root of hertz, it means my noise voltage is basically 1 nanovolt square for a bandwidth of 1 hertz, that is all it means, okay. So power spectral density is very important in general. Now if we come to device, and in this case specifically we are looking at MOSFET, so we have to understand that the channel current, the drain to source current, as we had discussed also in the MOSFET and in the gallium arsenide HEMT discussions, the source of the noise is the channel current itself, because that is like a resistance, the channel current is for flowing between the source and the drain, that is a resistance. So that resistance has to give rise to a thermal noise. So the thermal noise is the dominant noise in a MOSFET also, and you can see that if this is the drain and this is the source and this is the gate, you can model that in the output as a parallel, you can put that in parallel, and this is the quantity which represents the noise voltage between the source and the drain, that is that is the fundamental noise in the MOSFET, just like it is also in any MOSFET and other devices, where 4kT we know. Gamma is actually it's a coefficient. For a long channel device it could be 2 by 3, for a scale device it could go even up to 2. Gm is the transconductance, but more accurately it should be Gd naught, which is like the channel conductance. So this thermal noise in resistance, resistors, can either be modeled as a voltage source in series, for instance here, or it can be modeled as a current source in parallel. This is the Norton equivalent and this is the Thevenin equivalent, if you recall your undergrad electronics lectures. So this noise, the fundamental noise source at the output, can also be referred to the input as a series with the gate, and this becomes 4 kT gamma by Gm. This is you can refer it on the input side also, but this is something that is very important to understand. Now another very dominant source of noise is the gate resistance, because in a real RF device, specifically when you are talking about multi-finger devices and or long wide devices, then the gate metal resistance is a cause of worry, because in silicon devices typically people use polysilicon, and polysilicon has a reasonably higher resistance than metal, for instance. So W by L times this is the sheet resistance of the metal. You cannot do much about that because the metal will have its own sheet resistance, but W by L is very important. You want to keep this as low as possible, the gate resistance, because this will also create a thermal resistance. Now how much thermal resistance it will create? The gate, if the gate resistance is Rg, then the thermal resistance is not 4 kT Rg, but it is 4 kT Rg by 3. You see this 4 kT Rg by 3. Why? Because if you are feeding it from the one side, the gate is feeding the signal from one side. If you recall the distributed nature of the gate resistance, because it is a microwave frequencies and you are looking at a gate which is wide, this is the gate width by the way, correct. It is like a distributed line, it is a transmission line, and so if the gate is being connected from one side only, then the distributed analysis, the distributed propagation of the carrier analysis results in 4 kT, not 4 kT, R by 3 is the resistance, effective resistance. If you are feeding from both sides the gate, then it becomes Rg by 6, but typically devices are fed from only one side, of course the gate is on one side, so it is 4 kT by Rg by 4 kT Rg by 3. This is the resistance originating from the gate metal, and for a good MOSFET noise performance you want that this noise originating from the gate metal resistance should be very small compared to the fundamental noise in the channel of the device. The fundamental channel noise is 4 kT gamma by Gm, it was referred to the input side if you remember. So it should be, because the gate resistance is also here, the gate resistance is also here, you see this is the gate resistance, this is the gate resistance, because of which you have this gate noise, the noise because of gate resistance, and of course you are referring to the input, this is your noise referred to the input from the actual channel, correct. So you want that this quantity should be as less as possible, which means Rg by 3 should be as low as possible compared to say gamma by Gm, which means your gate resistance should be as small as possible and your transconductance should be as high as possible. Gamma is something that is coefficient, you cannot do much about it. So this is Rg, so this is basically a very important principle, that this condition should hold true so that the gate metal resistance should not kill your device noise performance. Now there is also a induced gate noise, if you recall in our discussion for gallium arsenide and gallium arsenide Hampton MOSFET discussions, we talked about this induced gate noise, which is basically the channel noise that is happening in between source and drain, gets capacitively coupled to the gate, and that gives rise to a noise in the gate. It is called gate induced noise, and the origin is the same, which is the current flowing in this channel. It is capacitively coupled to the gate, giving rise to another noise called the gate induced noise, but because the source is the same they are largely correlated and they are just 90° phase shifted because of the capacitive coupling, and so there is a correlation coefficient of course, and this is the gate induced noise. We do not have to worry about the expression so much, but beta is essentially a bias dependent parameter. This quantity arises from some kind of expansion, and this expression is valid for lower frequency, compared to the cutoff frequency you are looking at lower than cutoff frequency. But this gate induced noise is something we discussed in our MOSFET discussions also. So this becomes more prominent when you are talking about really high frequencies, but MOSFETs, and you can see that LDMOS do not go to super high frequencies, they are typically limited by 3 GHz or lower typically, so we do not much worry about gate induced noise most of the time. The last noise in MOSFET is the flicker noise, which we probably have not discussed in great details, but flicker noise, the origin of flicker noise is basically you have the silicon dioxide and silicon. So, this interface, there could be dangling bonds, right, there could be dangling bonds, there could be defects, there could be traps, there could be native oxide charges that are here in this interface of silicon dioxide. Okay. So, what happens is that because at the interface of silicon dioxide you form the inversion layer, which basically carries the channel charge. So, electrons that are moving can be trapped and detrapped by these dangling bonds, defects, traps, recombination centers, etc. Okay. So, this trapping detrapping can cause a noise, and that is precisely the flicker noise. Although there is another theory that says that there could be a reason of this flicker noise originating from mobility, electron mobility that fluctuates because of the gate voltage, because when you apply gate voltage, you change the gate voltage, the charge density in the channel changes, and as a result your mobility could also change. The fluctuations of mobility could give rise to flicker noise, but the dominant understanding is that it is because of the carriers getting randomly trapped, detrapped at the defects, dangling bonds, recombination center, etc., at the interface. Okay. So, this is loosely the expression for flicker noise, and you can see this has a 1 by f dependence, which means the flicker noise again Vn square, okay, noise voltage square. The flicker noise becomes weaker or less significant as frequency becomes higher, because with higher frequency 1 by f becomes smaller. So, this quantity becomes smaller. So, you can see flicker noise drops like that. Okay. So, only at very low frequencies your flicker noise becomes very important, which means at very low frequency when your signal is not changing as much, it is very low frequency, flicker noise can become the killer. But at higher frequencies, and by higher frequencies typically this could be between say around tens of megahertz to hundreds of megahertz. Okay. It depends. So, this is the corner frequency, the frequency at which the flicker noise meets the thermal noise. The thermal noise is constant with respect to frequency. If you plot thermal noise, okay, the thermal noise with respect to frequency is constant because it has all frequency components and it is called white noise. Okay, it is called white noise. So, the thermal noise goes like that, flicker noise goes like that. So, they meet at some point, that is called corner frequency. Above the corner frequency, which is this part, your thermal noise dominates, your flicker noise does not dominate. So, corner frequency matters very much. It is typically tens of megahertz to hundreds of megahertz, and so for gigahertz at microwave frequencies you are good, you do not care about flicker noise. However, because in many systems like oscillators, mixers, multipliers, etc., you may have lower frequencies come up, then you have to worry about flicker noise because of this harmonics and all these mixers, oscillators, etc. You may get desirable signal at lower frequency for some kind of up conversion, down conversion, etc., and the flicker noise could become important. So, you have to consider the flicker noise before dismissing them. Okay. This expression for the corner frequency tells that the corner frequency becomes higher if your GM is higher, and of course, this depends on these different parameters. Okay. So, typically at RF frequencies or microwave frequencies we may not be so much concerned about flicker noise, but it is important to know that. Here however, if you recall, one thing that is very important to note down here is that if you recall the spectral density of white noise of the thermal resistance, it was 4 kT/R. Now, if I integrate this with respect to frequency from 0 to infinity, 4 kT/R dF, it goes from 0 to infinity, that is your noise power actually, or you can say voltage, you can say the voltage power square. Okay. So, this 0 to infinity 4 kT/R, because you are going from 0 to infinity, it actually becomes infinity, which means the noise power corresponding to a resistor of R is infinity, which is impossible and which makes no sense, because the resistor also has noise because of the ambient temperature, which is finite. The ambient temperature is not infinite. So, how is that the noise spectral density or the power spectral density indicates that there could be an infinite noise power? This is because there is a flaw. This white noise is not purely white. Above around 1 terahertz, this 4 kT/R begins to drop in frequency. Above 1 terahertz, this is not a constant line anymore, it starts dropping. Okay. So, that is why the area is not infinite, it is finite. Okay. So, that is something we should generally keep in mind, but this is in general about white noise, and then this is about flicker noise, etc. Okay. Now, typically when the circuit is noisy, what people do is that they assume the circuit is noiseless, there is no noise, and they refer all the noise to the input of the device. This is your input of the device and this is your output of the device. So, at the input of the device you have a noise voltage source in series and a noise current source in parallel. You that is basically representative of the noisy circuit, I mean this entire thing. So what happens is that if you have a noisy circuit, it's for analysis purpose, it's best to basically define a noiseless circuit and put all the noise from the noisy circuit to the input side of the device or the circuit. You put it at the input side. So you have an input voltage noise, you have an input current noise, and that gives you the, on the input side, that gives you the noise. Okay, so it's a noiseless circuit with the noise referred to the input. Now why is the noise not referred to the output but referred to the input? Because if at the output, if you have a high noise, okay, if you have high noise at the output, we cannot be sure whether that high noise is because the system is fundamentally noisy or if the system has high gain, because when you have a noise at the input, the gain of the system will amplify the noise at the output. It will amplify the signal also, but it will amplify the noise also, correct. So a high gain also can give to a high noise at the output. So we do not know whether the high noise is because of a high gain or it is fundamentally high noise in the circuit. That is why it is better to refer everything to the input side, okay, it is referred to the input side, and this is the modeling people do the respect to the noise, okay. So now the small signal, maybe I can remove the annotation here, okay, one second. Okay. So if you look at the noise equivalent circuit, within the dash box is your intrinsic noise circuit. So what is outside the noise? You have an external gate resistor, and that corresponds to an external gate metal resistance thermal noise. There is a source resistance, external source may be a wire bond, may be a bond pad, and there is an external source thermal resistance. Similarly drain, okay, everything else is internal, you can see everything else is internal. What is the internal noise sources? Number one, there is a internal gate resistance which is internal to the gate metal in the active device, that gives rise to this gate metal resistance noise, thermal noise, and ideally we need it to be very small as we discussed. The second noise, and very important noise, is actually the drain, the noise in this between the source and the drain. It's referred, it's on the between the, essentially it's towards the drain terminal. This is your 4 kT gamma gm, correct. This is your thermal noise because of the current that is flowing where the channel of the device is modeled as a resistor. And of course you can have an induced noise which is precisely this. Everything else is fine. This is a capacitance, this is the output impedance, this is the output gate drain to bulk capacitance, etc., okay. And you can refer all the noise to the input by this source IN square in parallel and a VN square source in series. This is the input referred noise, okay, input referred noise, whereas the actual device you can say this is noiseless, there is no noise here. So you have a noiseless circuit or a device, and then on the input side you refer to this noise, okay. So this is how the noise signal modeling is done, I mean the small signal equivalent for noise is actually represented, okay. And the final thing is noise figure, which we have also discussed in our gallium arsenide based lecture discussions. Essentially whenever you have a signal in the input and you have noise in the input, there is a certain signal to noise ratio. Now there is an amplifier, for instance, it will amplify the signal but it will also amplify the noise. So the signal will amplify but the noise also will amplify. However, this system will add an additional noise because the system has its own noise, correct. So this is precisely what is happening. This is with respect to frequency, so at a certain frequency of course. So your signal to noise ratio has a power like that. If you have a gain of G, then both signal and noise will be amplified by the same amount, so it looks like the same, okay. It is a log scale, so that is why it looks like a smaller peak but actually is the same, okay. So it is amplified there. However, there is this additional noise that comes from the system or the amplifier, you can say the device, okay. So that adds additional noise as you going on. That is why at the output the signal to noise ratio at the output becomes worse compared to signal to noise ratio at the input. So signal to noise ratio at the input is higher, signal is better than the noise. At the output the signal to noise ratio becomes lower because there is more noise now. So this ratio is always more than 1. The ideal scenario is that this is equal to 1, and the log of this is called the noise figure. Without log it is called noise factor, and with log it is called noise figure. So the ideal case would be that if you have 0 noise that is added by the amplifier, which is practically almost impossible, but because and the system will add some noise anyway, even if it is very incremental. So the ideal case is that you have a signal to noise ratio at the input which is the same as the signal to noise ratio at the output. In that case your noise figure will be 0 dB, okay. That is the ideal case. However, you know, anything 1 dB or less than 1 dB is spectacular. People, it depends on frequency. If you go to higher frequency, if you recall in our MOSFET discussion, at higher frequencies your noise figure tends to degrade, which means the noise figure tends to rise. But the noise figure basically depends on this square root. This is the same expression for HEMT's MOSFETs also. Your gate resistance by GM. So, and there is also of course FT outside. So, you need to have a very good FT and you need to have very good GM, high GM, and the gate resistance should be minimum, then the noise figure will be as low as possible. Okay. So, that is why the gate length LG should be very low. We have discussed this in detail. A low gate length will give you high GM and also high FT. Okay. It will give you GM. See, FT also is very important, by the way. So, you need a good FT, you need a good GM. So, you need a very short gate length. Okay. You need a very short gate length. The width of the gate, this width W, the noise becomes worse actually if your width becomes larger and larger typically. So, the gate width also cannot be too large. Okay. So, with that we are at the end of this discussion on noise, but now we will move to LDMOS. Okay. So, we have discussed, what we have discussed so far is that we are talking about RF MOSFET. We talked about layout, parasitic capacitances, resistances. We talked about different extrinsic resistances, etc. We talked about the noise in today's lecture. Okay. We talked about SOI, which is silicon on insulator. What is very important and interesting to know is that typically when people scale down CMOS technology, 22 nanometer from 65, 45 etc. nanometer, they are making a platform which is more suitable for digital logic processing. Okay. And so, people are going to Tri-Gate, FinFET etc. architecture. It is not specifically made for RF, it is made for logic processing. However, people do implement RF circuits on that with very good performance and extremely good integration with all the digital part and the analog mixed signal and the RF part. RF part is also integrated, not all RF, but most of the RF can be integrated. So, the platform is also used by RF in a way, you can say. However, SOI or silicon on insulator, there are wafers, not there can be, there are wafers, there are technologies where the wafer is made with respect to only RF. So, you have extremely low loss, very good isolation, excellent isolation, no latch up etc. So, the SOI platform can be tuned only for RF, and very high performance RF devices on silicon CMOS, but on SOI are used for antenna beam forming IC. In wireless communication, for instance, you need low noise amplifier antenna switches etc., where you need outstanding performance in 5G and wider other things. There people use RF SOI. Okay. Cost does not matter as much, the RF people use RF SOI, and this is whatever we discussed now was actually generic in terms of noise for a MOSFET. I am not talking specifically for a Tri-Gate or a scale MOSFET, but generic MOSFET. Now we will move to LDMOS. What is LDMOS? LDMOS is basically the high voltage cousin or the high voltage counterpart of RF CMOS. Okay. So, what happens is that this is all something we discussed in the last lecture. Okay. So, this is your LDMOS. So, whatever we discussed till now in terms of RF CMOS or RF MOSFET, SOI etc. are all typically low voltage, low power. By low voltage, low power I mean if you use a handheld electronics, your supply voltage could be 3.3 volt, maximum maybe 12 volt in some cases, okay, in some kind of special application, but typically these are at low voltage, high integration, they exist in conjunction with the densely packed digital electronics, the digital circuit. But LDMOS is not in that segment. LDMOS is actually for higher voltage RF. By higher voltage I mean say 28 to 32 volt. 28 to 32 volt is the drain bias, okay, that is a different ball game. You are looking at 28 to 32 volt drain bias, which means the breakdown should be at least around 65 volt. Remember, it should be twice because the drain can swing this way, typically. So, if this is 28, then you need this to be at least 56. If this is 32, it should be 64. So, that is why around 65 volt. Okay. This is a different category of devices, although this is MOSFET, but it is slightly different. It is called LDMOS. L stands for lateral, okay, and D stands for diffused. So, it is a laterally diffused MOSFET which is specifically designed to block higher voltages or higher breakdown while not sacrificing the RF performance, so that you can get good RF output power, okay, with associated gain, linearity, okay, with power added efficiency, correct. All these quantities should also be acceptable, but at the same time your breakdown voltage is high, so you can bias at higher voltage. So with higher voltage your output power will be high. So LDMOS is a very dominant and competing technology for mobile base station, okay, or you can say the cell phone towers, you can say, as you can say, the mobile base stations need LDMOS devices, although this is being increasingly challenged by GaN HEMT. Okay, GaN HEMTs can offer much superior performance on all yardstick, output power, gain, efficiency, linearity is a different ball game. However, and footprint, of course, the footprint, GaN can outperform LDMOS on all counts. However, LDMOS offers cost advantage, volume manufacturability, and thirdly integration. Integration is a very important aspect, because if you can make LDMOS on the same wafer as your digital logic, then you can actually integrate the power amplifier with the entire CMOS front end, okay, and that is something unprecedented. You cannot do that on gallium nitride, because gallium nitride is not used or useful for making the digital logic, you know, analog mixed signal is not implemented in gallium nitride. So LDMOS has those advantages of integration, but it is for high voltage application and it is extremely useful for mobile wireless communication base station, even strategic sectors like radar, satellite communication, etc. LDMOS is very promising, and it is widely used today as we are talking today, okay, and it is continuing to evolve. Every single generation of LDMOS is evolving to reach to reach gallium nitride, or to bridge the gap between the performance of LDMOS and gallium nitride is actually shrinking, although it is very improbable for LDMOS to beat gallium nitride, but the gap is shrinking. LDMOS is approaching gallium nitride on many counts, slowly, step by step, because of the advanced foundry processes, because of the advanced integration scope. LDMOS has these unique advantages, okay, and the fabrication of LDMOS is very proprietary. You cannot get details of LDMOS fabrication on the internet. It's there are patents, of course, but it's very high, you know, of importance to industry, the way LDMOS is fabricated, but the design and other things we can discuss in this lecture. That is what we are going to do in this lecture, okay. So what I am showing you here is typically for power amplifier, in RF power amplifier, what is the different frequencies and what are the different powers on the y axis and the competing technologies. So of course for low power, when I say low power I mean tens of milliwatt, maybe 100 milliwatt, RF CMOS, could be CMOS, even SOI, is something that, and this is power amplifier, this is not low noise amplifier by the way, at the very high frequency you can actually go, and it can give very competitive advantage. Silicon germanium, we have not talked about that yet, we will talk about that in bipolar devices next week. Silicon germanium can give superior performance on the speed side, okay, it can give you a very good speed performance advantage, gain, etc. LDMOS comes at higher power, you see this is the segment of LDMOS, it comes at few watts to few hundred watts. People have even made, and this 7 volt means 7 volt drain bias, 28 volt means 28 volt drain bias, people even have 50 volt LDMOS now, which means the LDMOS can be biased at 50 volt, okay, just okay, and people recently have even made 65 volt LDMOS, but the frequency is low. So you can see that frequency is probably around 2 gigahertz. In all commercially LDMOS is very competitive at around 3.5 gigahertz or lower frequencies. Above that LDMOS rapidly loses its advantages, okay, although people have done extensive research and there are papers on LDMOS performing at X band at even 12 gigahertz, people have shown competitive performance, but commercial adoption, because of many issues, you know, the performance, overall performance degrades after 3.5 gigahertz, okay. So typically till 3.5 gigahertz LDMOS is like the king for high power, you know, if you want few watts, few tens of watts or few hundreds of watts or even kilowatt, you can get 1.8 kilowatt LDMOS at sub 1 gigahertz, okay, at sub 1 gigahertz or close to 1 gigahertz you can get 1.8 kilowatt LDMOS also, with very good gain and efficiency essentially. So many applications actually, you know, science, medicine, industry, ISM call it, avionics, military, satellite, many things benefit a lot. Typically base station, wireless base stations use a power, the power amplifier needs a power of around 300 to 400 watts, and so they are biased at 28 volt usually, and that is your LDMOS space. You can see that gallium nitride is targeting at higher frequency at higher power. So, if you want tens of watt to hundreds of watts at above 3 gigahertz, 6, 7, 10 gigahertz etc., then gallium nitride is a dominant technology. Okay. Indium phosphide is low power but super high frequency, 100 beyond 100 200 gigahertz. Okay. Indium phosphide low power, very low power. Okay. So, the difference between CMOS and LDMOS is that LDMOS is high voltage, CMOS is not. So, LDMOS design, the fundamental design enables a high voltage, that means between the gate and between the drain, this is the gate and this is the drain. You do not have self aligned gate drain in a very close by each other like in a CMOS, but you intentionally have a drift region here. A drift region will block the voltage and it will give the LDMOS the voltage advantage, it gives the voltage advantage. Okay. So, essentially because the breakdown field of silicon is much lower, say 10 times lower than gallium nitride. So, if you want to block, if you want to operate the device at say 50 volt, which means you want a breakdown of 100 volt at least. Okay. To have 100 volt breakdown, the spacing between the gate and the drain LGD has to be large, it has to be large to enable 100 volt breakdown. And if the LGD is large, then electron velocity and mobility are finite. So, your cutoff frequency will drop and so your power will drop, gain will drop. That means your cutoff frequency will drop so much that for 50 volt bias or even 28 volt bias, getting power beyond 3.5 gigahertz becomes a challenge because your cutoff frequencies are low. However, in gallium nitride, because the breakdown field can be much higher, to block 100 volt you can have a drain which is much closer to the gate. It can be very close, and still, by close I mean couple of micron, few microns, it can still block 100 volt. So, your cutoff frequency does not degrade because the gate and the drain are very close. So, your performance at 6 gigahertz or 10 gigahertz or 18 gigahertz also is much better than silicon LDMOS devices. Now, although we keep hearing the term gain, linearity, noise etc., noise does not come in so much in power amplifier here. You know, the modern wireless communication, specifically with respect to the handheld smartphones or other handheld gadgets, they have become so stringent in terms of battery usage, battery lifetime, okay, and the power consumption etc., and increased bandwidth, increased functionalities in the smartphone, that the constraints that are put on the power amplifier designer are increasing with every generation. And these constraints that are put by the system on the power amplifier are often contradictory or conflicting to each other. You want high gain, you want high power efficiency, you want high output power, you want low footprint, but these are conflicting goals. Okay. If you want very good linearity, you are going to sacrifice efficiency, and if you want very good efficiency, you are going to sacrifice linearity. So, conflicting goals have to be accommodated by the power amplifier designer. It is a very challenging task because the power amplifier is the most important unit that will decide your battery lifetime in the cell phone. Okay. So, it is a very important part. So, in specifically for power amplifier we are talking about LDMOS. Okay. So, with that we will end the class today here, lecture 38, where we talked about noise and then we introduced LDMOS, although we have not gone to the physics of LDMOS, but we are good. So, we are ending lecture 38 here today. We have 2 more lectures where we will dedicate exclusively on LDMOS. Okay. We will talk about LDMOS physics, practical aspects, commercial ones etc., etc. Okay. So, thank you, I will see you in lecture 39.